Hey everybody. So this is the second part in my chi-squared goodness of fit notes. The first part kind of explains an overview of how we're going to set this up and how we're going to work through a goodness of fit test. Um, this video, I'm going to work through an actual example. So hopefully some of the confusion and questions we have can be a little bit cleared up come this video. So in a recent year at the 6 p.m. time slot, television channels 2, 3, 4, and 5 captured the entire audience with 30%, 25%, 20%, and 25% respectively. So that means that's kind of their share of what people are watching. 30% of people are watching channel 2, 25% of people are watching channel 3, etc. During the first week of the next season, 500 viewers were randomly interviewed. The actual observed numbers are as follows. So we have a table here. Our sample, we had 139 watching channel 2, 138 watching channel 3, so on and so forth. So the question is, do these numbers indicate a change? Are the differences significant? So what we're doing is we have an observed sample, and we're wanting to see, does this sample match up with the hypothesized distribution? So they want to know, are we changing from this hypothesized breakdown? So we're going to perform a chi-squared goodness of fit test. So what I'm going to do is I'm going to do the option where I do not have to do a parameter. I'm just going to go straight to the hypothesis. So I'm going to start with the null hypothesis here. And what we're going to say is we're going to say our distribution follows the distribution of viewers at the 6 p.m. time slot. So we're going to assume in the null hypothesis that our breakdown matches what should have happened at that 6 p.m. time slot that was previously recorded. What we're trying to prove here is that our distribution is different or has changed or is not the same as the 6 p.m. time slot. So we're setting out to try and see this distribution does not actually match up with that breakdown. So in order to do this, before we could get a chi-square test statistic and have faith in those numbers, we need to make sure our assumptions all check out. So again, the first two are very routine with what we've been doing with all of our hypothesis tests. It's the third one that we really need to pay attention to. So randomization and 10%. So our 500 viewers were randomly selected. And we hope here our 500 viewers is less than 10% of all the possible viewers of these television stations. And then our third assumption that we need to tackle here, remember this is the one that switches out kind of from test to test, is we need to make sure all of our expected counts are at least 5 or greater than or equal to 5. This is something that we do need to show somewhere in this problem. What I do is I put it pretty close to where the observed values are at. So I'm going to make a row here for expected. So here's what we're going to use. We're going to use our sample size, which that was 500, and we're going to use these hypothesized distributions. So really what I'm going to be doing here is I'm going to be taking n times p. So I'm going to take 500 times 30%, because 30% of these folks should be on channel 2. So if you take 500 times 0.3, which is 30%, 500 times 0.3, what you're going to get is 150. So we expect 150 of the 500 to be watching channel 2. 150 over 500 should give you 30%. We're going to continue that pattern, 500 times 0.25. That is going to give me 125 viewers. So we expect 125 to be watching channel 3. 500 times 0.2 is going to give me 100. And then 500 times 0.25 is going to give me 125. So you can already see how my observed values kind of relate to my expected values. To an average person, they would look at that and be like, oh yes, they've of course changed. But we actually need statistic and a test statistic to actually figure this out for us. So looking at those expected counts, 150, 125, 100, 125, we do meet this third assumption. All expected counts are at least 5. And again, you do need to show that on there. Don't just make it some magical number that we don't really know whether they are or aren't. And you'll see here in a little bit, we actually need to know these numbers to actually perform these calculations. So the name of this test is the chi-squared goodness of fit test. And then we're going to do some calculating. So I'm going to show what this looks like calculated by hand. And then I'll show you how the calculator can kind of speed this up a little bit for us. So chi-squared equals a summation of, again, we're going to take our observed minus expected, square it, and divide it by expected. So I'm going to show you by hand the first two calculations, and then I'll jump on the calculator and show how we can knock this out pretty quick. So I got to go down through this entire table, take the observed minus the expected, square it, divide it by expected. So the observed is 139. The expected is 150. So I'll be taking 139 minus 150, squaring it, and dividing by 150. And then I'm going to keep progressing. I'm going to add this up because of the summation, move on to the next cell. So 138 and 125. We observed 138. We expected 125. So 138 minus 125. Square it, divided by 125. Now here's the thing you should be thinking about is, man, if I have a long table, do I have to write out all these calculations? So imagine if we were checking like 20 different channels in the distribution of viewers on those. You do not need to write out all 20, okay, or however long it is. You just need to show a few, and this illustrates to any grader that I understand how this formula works. I'm showing you how the formula works. I don't need to sit here all day and write it all out. So we're going to do a plus ... So if you're doing it by hand, would you actually have to figure that all out and figure every single one? Likely, but we're going to use a calculator. So I'm going to put ... an equal sign, and I'm going to show you how the calculator can tackle all of this for us. So in your calculator, kind of where we live with these hypothesis tests, we hit stat, we go over to tests, a whole bunch of tests that we've used so far in there, but if you keep scrolling down, you're going to see two different chi-squared tests. You're going to see a chi-squared test and a chi-squared goodness of fit test. That's what we want. It's going to ask you for a list that has your observed values, a list that has your expected values, and we're going to need to get the degrees of freedom. So I'm going to go ahead, I'm going to do the degrees of freedom on my paper, and then I'll show you how to do these two lists again, and then we'll calculate and wrap this all up. So remember the degrees of freedom, it is not n minus 1. So don't confuse this with t. We aren't doing n minus 1. We're taking the number of categories and subtracting 1. Well, the number of categories here, well, I have one category, channel 2, another category, channel 3, another category, channel 4, and then our final category, channel 5. So I have 1, 2, 3, 4 categories. So I'm going to be doing 4 minus 1, which gives you a degrees of freedom of 3. So back to the calculator, I need to go and figure out my observed values in list 1, my expected values in list 2, and then I can come back and calculate. So again, to get your list, stat, edit. In list 1, I typed in all of my observed counts, 139, 138, 112, 111, and then my expected counts, which I had calculated, 150, 125, 100, 125. So now when I go to the chi-squared test, goodness of fit, I have the observed, I have the expected, degrees of freedom of 3. We can now calculate. So what I get is a chi-squared test statistic of 5.16, or we can round that to 5.17. It's going to give you your p-value. It's going to tell you the degrees of freedom. And then there's this other piece here, which I'll talk about here in a second. I want to finish this out, and then we'll come back to this. So 5.17, it did tell us our p-value. So what I'm going to do is I'm going to draw our chi-squared distribution. What we're going to do is we're going to have a cutoff towards the right of 5.17, and we're always going to be taking the area to the right. So I'm going to be finding the probability that chi-squared is greater than or equal to this 5.17 value. We're always taking it to the right. We're never going to be in between or area to the left. It's always to the right, which is nice. Our calculator tells us this p-value is 0.1599. So if you want to round that, you can. If you just want to say, hey, let's just stick with 1.1599, you can. Okay. If you were going to do this with the chi-squared table, which I have just the textbook one in front of me, what you would do is you would have your chi-squared test statistic, 5.17. You would use the table, go to your degrees of freedom, which is 3, and then you're going to go across until you find in what range is my chi-squared test statistic in. Again, it was 5.17. So if I'm in degrees of freedom 3, 5.17 would fall between these two values. So therefore, I know my p-value is between 0.15 and 0.2. Okay, 0.15 and 0.2. Again, there's a chi-squared table that would be available to you. You're going to have a different row depending on the degrees of freedom. You just find your degrees of freedom, figure out between which two is your test statistic in, and that will tell you where's your p-value at, between what range. So we know it's between 0.15 and 0.20, but again, my calculator kind of helps me out there and says, hey, it's 0.1599. So I'm going to use the traditional alpha of 0.05. So if I have an alpha of 0.05 and this p-value is 0.1599, we're going to fail to reject the null hypothesis. And the reason for this is our p-value is not less than our significance level of alpha equals 0.05. So I cannot reject this idea that our distribution follows the distribution of viewers at the 6 p.m. time slot. I didn't find enough to reject this idea. So we can comment on our alternative hypothesis. We did not prove enough, so we have insufficient evidence to say our distribution, when I say up here, our distribution is different than a 6 p.m. time slot. So we didn't show enough to say our distribution of 500 viewers is that different from the 6 p.m. time slot. So they're asking, hey, do these numbers represent a change? There is no change. So there's no indication there. Okay, so that is a full chi-squared goodness of fit test written out. One last thing I want to show you is there was this thing in the calculator that says CNTRB. That is contributions. So how you could follow up here is if, say we did find a difference, the calculator can help you figure out, okay, which channel or which category contributed the most to this difference. So if you hit an arrow to the right, you're going to see 0.8066. That's how much contribution to the chi-squared test statistic this 2 had. Then we have a 1.35, so this contributed 1.35, then 1.44, then 1.568. So if there was a difference, you're looking for contributions here. Who had the most difference that contributed to us to rejecting if we would have done that? So since the final number was the one with the largest contribution, the biggest culprit would be channel 5 here, okay? So channel 5 would be the one piece that you would look a little bit closer at if we had rejected. We didn't here, we failed to reject, but if we had rejected the null hypothesis, I'd be taking a closer look at channel 5 and wondering, why did that channel change the most on the distribution? Okay, so that again was a chi-squared goodness of fit test. You can run through this video again, pause it, take notes on what you need, but that is a complete chi-squared goodness of fit test.